We shall discuss Chapter 5, Module 2. In this module, we shall learn homotopy of two maps and also discuss various situations where two continuous functions are homotopic. We start with discussing homotopy of two continuous functions from a totally informal point of view. Suppose we are given two continuous functions, one is f from x to y and another continuous function g from x to y. The question is, can we deform f continuously into g? If the answer is yes, then f is said to be homotopic to g. Now, if I look at this diagram, suppose we are given two functions f and g, they are continuous functions from a space capital X to another space capital Y. Now, in the figure, we observe that this is the image of x under the map f and this is the image of x under the map g. So, the question is, can we take this f, this image portion and deform it continuously to get into this g? In this case, from the figure, we feel that yes, we can. But we have to rather formalize the term deform f continuously into g. What do we mean by that? For that, actually, we are looking for a family of continuous functions phi t from x to y, where t is varying continuously in the interval 0, 1, such that the initial position of phi, that is phi 0, should be f, final position of phi, that is phi 1, is g, and the process is that phi t should change continuously as t varies from 0 to 1. Further, we need to formalize once again phi t changes continuously with t. What do I mean by that? So, for formalizing phi t changes continuously with t, we make use of the product space x cross I, where I stands for the closed interval 0, 1. So, we give the formal definition of homotopy this way, that given two continuous function f and g from x to y, f is said to be homotopic to g, denoted by f homotopic g if there exists a continuous function capital F such that fx0 is small fx and fx1 is equal to small gx for all x belonging to capital X. The domain of capital F is the product space x cross I and the range is capital Y, and this capital F is called the homotopy. If the function f is homotopic to a constant map, then that function is called null homotopic, and we denote it by f homotopic to 0. Now, let us take one example. Suppose f is a function from Rn to Rn which takes any x to the same x. That means it is the identity function. And we take another function g from Rn to Rn, which takes all the points of Rn and map it to a single point 0 in Rn. That means it is the constant function 0. So now if we define the map capital F from Rn cross I to Rn by f of xt is equal to 1 minus t of x, then of course capital F is a continuous function, and fx0 is equal to fx, fx1 equal to gx. So all the conditions for homotopy are fulfilled, and therefore capital F is a homotopy. Now the question is f the only function which satisfies these conditions? Answer to this question is definitely no. We can also think of another function, capital H, from Rn cross I to capital Rn, given by hxt is equal to 1 minus t square into x. Then this capital H also serves the same purpose, because capital H is still continuous, hx0 is fx and hx1 equal to gx. Therefore, there are several ways a function can homotope to another function. Let us take the question 2. Is there anything special about the chosen functions f and g on Rn? The answer is again no. Let's take this example that I take any two continuous functions f and g from Rn to Rn. We are talking about any two continuous functions f and g, no specific ones. In this case also, define a function capital F from Rn cross I to Rn given by fxt is equal to tgx plus 1 minus t into fx, where x varies over Rn and t varies over I. In this case, capital F being convex combination of fx and gx, it is continuous, and fx0 equal to fx, fx1 equal to gx. So this capital F is a homotopy between f and g. Now looking at this example again, there is no speciality of Rn in the domain. We can easily replace Rn by any topological space X in the domain. In that case also, this example gives that f and g are homotopic maps. Now what is so special about Rn in the codomain? We only need the fact that the convex combination of 2 points of Rn should be inside Rn. So that means given 2 points in Rn, we want to join them by a straight line, and what we want is that line should be within Rn. All the points on this line should be within Rn. So that is what we mean by convex combination. So we get a more general example. Topological space capital Y, we take a convex subset Y of Rn. We suppose that f and g are two continuous functions from x to y. Define a function capital Y f from x cross I to y by fxt is equal to tgx plus 1 minus t of fx. Then, since y is a convex subset of Rn, tgx plus 1 minus t of fx is within capital Y. So this function is defined and it is a continuous function satisfying the rest of the two conditions for f to be homotopy. So f and g are homotopic maps. The homotopy described in all these examples is known as straight line homotopy. However, convexity of the codomain space is not at all mandatory for any two functions to be homotopic. Let us see an example. If we start with a topological space X, we take an open upper hemisphere H2 of unit radius. We take two continuous functions f and g from X to H2 and define capital F by the formula fxt is equal to tgx plus 1 minus t of fx whole thing divided by norm of tgx plus 1 minus t of fx. Then this capital F is also a homotopy. If we put t equal to 0, we get the function f back. If we put t equal to 1, we get the function g back. Now, of course, we have to verify that fx and gx can never be antipodal points. The denominator is not vanishing. Now, what do I mean by antipodal point is that they are not diametrically opposite points, and that is not possible because we are taking only the open upper hemisphere of unit radius. Therefore, capital F is serving as a homotopy between f and g. From all these examples, one may have an impression that the codomain space must be either Rn or any subspace of Rn, but it is certainly not. We have some examples we can see in the course that there are several examples of homotopic maps having codomain space as any arbitrary topological space. Secondly, while using straight line homotopy, one must be very careful, because for using straight line homotopy, we must have the codomain space as a convex subset of Rn. So, if a function f is given from capital X to capital Y and another function g is given from capital X to capital Y, where this Y is any arbitrary topological space, then we cannot use straight line homotopy to establish that they are homotopic. Now, we show that being homotopic too is an equivalence relation. Now, for that we state the theorem. Suppose we are taking a collection of all continuous functions from a topological space X to another topological space Y and define a relation on Cxy by f is related to g if and only if f is homotopic to g. We shall show that this relation is an equivalence relation. For proving this to be an equivalence relation, we have to prove that it is reflexive, it is symmetric, and it is transitive. So, how do we prove that it is reflexive? We take any function from Cxy. So, f is a continuous function from x to y. We define the map capital H from x cross I to y by hxt is equal to fx for all x belonging to capital X and for all t belonging to I. Then f is homotopic to f by the function capital H. Now we want to show that it is symmetric. So we start with any two continuous functions f and g from Cxy. It is given that f is homotopic to g. So if f is homotopic to g, then certainly we are going to get a function capital H such that hx0 is fx and hx1 is equal to gx. Now let us define a map capital F with the help of the given function capital H, that fxt is equal to h of x1 minus t for all x belonging to capital X and for all t belonging to capital I. Then of course f is a continuous function such that if x0, if I put t equal to 0 in the expression of f, we get hx1, which is actually gx. And if we put t equal to 1 in the expression of fxt, we get fx1 equal to hx0, which is actually fx. So that establishes that g is homotopic to f. This relation is transitive. Suppose f, g, h are three functions taken from Cxy such that f is homotopic to g by h1 and g is homotopic to h by h2. We want to define a function capital H from x cross I to y such that hx0 is fx and hx1 is equal to hx. So for that, we want to split the interval 0, 1 into two halves. In the first portion, that is from 0 to half, we define h by means of capital H1, and in the second half, that is when t varies from half to 1, we define capital H by means of h2. So we define the function capital H from x cross I to y by hxt is equal to h1 x 2t when t varies over 0 to half, and h2 x 2t minus 1 if t varies from half to 1, and for all x belonging to capital X. Then using pasting lemma, since h1 and h2 both are continuous in the closed intervals 0 half and half 1 respectively, and at the point t equal to half, h1 x 2t and h2 x 2t minus 1 share the same value. So by pasting lemma, h is a continuous function and hx0 is equal to fx and hx1 is equal to small hx for all x belonging to capital X. And that gives a homotopy between f and g. So that homotopy is an equivalence relation can be used effectively to establish a very useful result regarding composition of homotopic maps. Suppose we are given two functions f1 and g1 from x to y, and it is known that f1 and g1 are homotopic. And also a pair of functions f2 and g2 are given from y to z, and it is known that f2 and g2 are homotopic. Then the result says that if we compose the function f2 with f1 and compose the function g2 with g1, we are going to get homotopic functions. That means f2 composed f1 will be homotopic to g2 composed g1. We sketch a proof of this result now. Suppose f1 and g1 are homotopic by the homotopy h1, f2 and g2 are homotopic by the homotopy h2. Then we have this nice diagram. h1 is a continuous function from x cross I to y, f2 is a continuous function from y to z. So the composition of two continuous functions is continuous, and thereby f2 composed h1 is continuous from x cross I to z. Also, if we evaluate f2 composed h1 at the point x0, we get that it is f2 composed f1 of x, and if you evaluate the function f2 composed h1 at the point x1, then we get f2 composed g1 x for all x belonging to capital X. Hence, f2 composed f1 and f2 composed g1, these two continuous functions are homotopic via the homotopy f2 composed h1. Now we define the map psi from x cross I to y cross I given by psi xt is equal to g1x comma t. Then we again have this commutative diagram that psi is a map from x cross I to y cross I, which is continuous. H2 is a continuous map from y cross I to z. So their composition H2 composed psi is a continuous function from x cross I to z. Therefore, if we take that function H2 composed psi as capital H, then it is a continuous function satisfying the condition that hx0 gives me f2 composed g1 x and hx1 is equal to g2 composed g1 x for all x belonging to capital X. Hence, f2 composed g1 is homotopic to g2 composed g1 via the homotopy capital H. Now, if we take these two results, then we have already seen that f2 composed f1 was homotopic to f2 composed g1, and now f2 composed g1 is homotopic to g2 composed g1. So combining these two as homotopy is a transitive relation, f2 composed f1 will be homotopic to g2 composed g1. Now we conclude this by defining homotopy relative to a set. What do we mean by that? Intuitively, while deforming f into g continuously, if a set of points of the domain remains unaltered, or rather unaffected by the deformation, then the homotopy is known as the homotopy relative to that particular set of points. So if we formalize this intuitive idea, then we get the definition of relative homotopy, that given a subset A of x, given two functions, continuous functions f and g from x to y, if capital H from x cross I to y is a continuous function such that hx0 is fx and hx1 equal to gx for all x belonging to capital X, and further at every point A of a capital A, hat is equal to fa and that is again equal to ga, then capital H is called a relative homotopy, or f is said to be homotopic to G relative to the set A. If in particular we choose A as an empty set, then the definition of relative homotopy reduces to that of a homotopy, because there is no point in capital A and therefore there is nothing to satisfy the last condition. However, there are examples which show that homotopy may not imply relative homotopy. Later on in this course, we shall see that we need some special type of relative homotopy called path homotopy, which are required to construct fundamental groups. With this note, we conclude this module.